Hi friends, welcome to the lecture of linear algebra. Today we are going to study the last point of the chapter, which is a T conductor of alpha into W. Alpha into W. Okay. Now let us see what is a T conductor of alpha into subspace W. Let W is a invariant invariant subspace of of V under linear operator T. Okay, let alpha belongs to V any any vector. Now, the T conductor of alpha, the T conductor of alpha into invariant subspace W is the set S of alpha W, which which consists of all all polynomials g of s over f such that g of t of alpha is belonging to W. So, if W be any invariant subspace of a vector space V under the linear operator T and alpha belonging to V be any vector, then the T conductor of alpha into a subspace W is the set St of, which is denoted by St of alpha W, which consists of all polynomials g of x over the field f, such that Gt of alpha is belonging to subspace W. That is, in general, this St of alpha W is nothing but a set, that is St of alpha W is nothing but a set which contains all polynomials g of x belongs to the ring of polynomials f of x, such that gt of alpha is belonging to W. This is nothing but the T conductor of alpha into a subspace W. As the linear operator T is filled through most of the discussion, so here we can drop this subscript T and we can denote this St of alpha W as also by S of alpha W. Since already we know that T is a linear operator on vector space V, therefore we can operator T is filled through many of the discussion. So there is no need to write this subscript T. We can denote it by also S of alpha W. Okay. Now the next definition is ideal. Before that, let us see whether it is possible that the set St of alpha W is an empty set. We have to check whether St of alpha W, which is nothing but S of alpha W, is whether phi or not equal to phi. Let mx be the minimal polynomial. Let mx be the minimal polynomial for linear operator T. As mx is the minimal polynomial for linear operator T, then this mx annihilates the linear operator T. Annihilates means m of T is nothing but 0. Since mx is the minimal polynomial for the linear operator T, which implies mt will be equal to 0. That is, mt of x is equal to 0 for all x belonging to V, since mx annihilates the linear operator T. As m of x equal to 0 for all x belonging to V and W is a subspace of a vector space V, then each element of W is a element of V also. Then empty of alpha is equal to 0 for all alpha belonging to W. Since W is a subspace of vector space V, it implies W is subset of V. And empty of x is equal to 0 for each x belonging to V. Then empty of alpha must be 0 for each alpha belonging to W. Okay. So here we get now 0 is belonging to W. Since W is a subspace. So if we take any alpha belonging to W, then we get a polynomial Mx such that empty of alpha is equal to 0 and the 0 is belonging to subspace W. Then by definition of S of alpha W, it contains all the polynomials g of x belonging to f of x such that gt of alpha belonging to W. Here empty of alpha equal to 0 and 0 is belonging to W. Then this Mx is a member of this S of alpha W. That is st of alpha W, which implies Mx is belonging to S of alpha W by the definition of T-conductor. So, minimal polynomial is always a member of this S of alpha W, that is T-conductor of alpha into W or T-conductor. So, which implies Mx is always member of T-conductor of alpha into W, which implies S of alpha W is not equal to 5 since it contains always one minimal polynomial. So this S of alpha W is not equal to 5. Okay. Now we have to see one definition. What is an ideal? Actually, in abstract algebra, we know that ideal means nothing but if suppose we have to prove this I is an ideal, then we have to prove this I is a left ideal as well as a right ideal. Then we say that I is an ideal of a ring R something. So here we have ideal. Let F be a field. Let F be a field. An ideal. An ideal is ring of polynomials F of X is a subspace capital M of F of X M of Fx such that F into G is belonging to subspace M whenever F is belonging to ring of polynomials and G is belonging to M. Okay. So, if F be a field, an ideal in F of X, this F of X, an ideal in F of X is a subspace M of ring of polynomial F of X such that F into G is belonging to M whenever F is belonging to ring of polynomial Fx and G is belonging to M. Then we say that this subspace M is an ideal of a ring of polynomials F of X, which is actually equivalent to our definition of ideal. In ideal, we will prove we said M is an ideal if it is both the right ideal and left ideal. Here we have proved this is a subspace. As it is a subspace, then it holds all the properties of left ideal and right ideal. Hence, this one is the definition of ideal. Now we have to prove one result depending on this definition. Let W is invariant subspace of linear operator T, invariant subspace of T, then W is invariant under every polynomial in T. Thus, for each thus for each alpha belonging to vector space V, the the T conductor S of alpha W is an ideal in the polynomial algebra polynomial algebra f of x. So here we have to prove this theorem. It is given that W is an invariant subspace of a vector space V under the linear operator T, and then we have to prove that this subspace W is invariant under every polynomial in linear operator T. That is, we have to take one alpha belonging to W, and we have to prove that the polynomial in T, that is something f of T, is also belonging to this W. Then we say that W is invariant under every polynomial in the linear operator T. And from this, if for then we have to next prove thus for each alpha belonging to V, the T conductor is nothing but S of alpha W is an ideal. That is, this S of alpha W holds this condition. To prove that S of alpha W is an ideal, first we have to prove S of alpha W is an subspace of a ring of polynomial f of x, and after that we have to prove this condition. That is, f into g is belonging to S of alpha W whenever f of x is belonging to ring of polynomials f of x and g is belonging to our S of alpha W. Okay, let us see proof. Okay, given that W is invariant subspace of linear operator T. As W is invariant subspace of T, then by the definition of invariant subspace, T of alpha is belonging to W for all alpha belonging to W, which is from definition of invariant subspace. Now, as T of alpha is belonging to W, then T of T alpha is again belongs to W for all T alpha belonging to W. Since W is invariant subspace of T, then T of alpha is belonging to W for each alpha belonging to W. As T of alpha is belongs to W, then T of T alpha is again belonging to this subspace W. Since W is an invariant subspace, which implies T square of alpha is belonging to W. Similarly, T cube of alpha is nothing but T of T square of alpha is belonging to W. Since T square alpha is belonging to W, as T square alpha is a member of W, then T of T square of alpha is again in W. Since W is an invariant subspace of linear operator T, which implies T cube of alpha is belonging to W. Similarly, we can generalize it up to kth state. Then Tk of alpha is belonging to W. Okay, as here T of alpha is member of alpha is a member of W. T of alpha is a member of W. T square alpha belonging to W, and up to so on Tk to the power T to the power K of alpha is again belonging to W, and W is a subspace. As W is a subspace, then W is closed under addition and scalar multiplication. Then, as these T of alpha, T square alpha, up to so on T to the power K of alpha is belonging to W, then its addition must be belonging to W, which implies T to the power K of alpha plus T to the power K minus 1 of alpha plus up to so on T square alpha plus T of alpha plus I of alpha is belonging to subspace W. This is an identity operator. Okay, so which is nothing but T to the power K. Since this sum is belonging to W, since W is a subspace, as it is a subspace, then it is closed under addition. Okay, T to the power K, which is nothing but T to the power K minus 1 plus up to so on T square plus T plus I of alpha. Each T is a linear operator. It is again belonging to W. Let us now, it is a polynomial in T of degree K. So it is nothing but f of T of alpha is belonging to W. So here we have taken one alpha belonging to W, and we and we have proven f of t of alpha is belonging to W, where f of t is a ring of, it is a polynomial in linear operator t. Alpha is belonging to W, then f of t of alpha is belonging to W. Then from this we say that W is invariant under every polynomial in T, which implies W is invariant under every polynomial in linear operator. Okay, now we have to prove the next part. That is, we have to take one alpha belonging to vector space V, and we have to prove that the T-conductor S of alpha W is an ideal in the ring of polynomial f of x. Let alpha belonging to V be any vector. Any vector. Now we have to prove that the T-conductor of alpha into W, that is T-conductor of alpha into W is nothing but S of alpha W, and which is nothing but it contains all f of x belonging to ring of polynomials fx such that ft of alpha is belonging to subspace W. Okay, is an ideal in fx. Here we have to prove this statement. Now we have to prove that this S of alpha W is an ideal in fx. Now again, by definition of ideal, first we have to prove that this S of alpha W is an subspace of a ring of polynomial fx, and we know that fx is said to be S of alpha W is said to be a subspace of ring of polynomial or vector space f of x if it is closed under the operations defined on its vector space fx. So let f of x comma g of x belonging to S of alpha W. And we know that S of alpha W contains all the polynomials belonging to ring of polynomials such that ft of alpha is belonging to W, as fx and gx belonging to S of alpha W, which implies ft of alpha is belonging to subspace W, and gt of alpha is belonging to W. Now it remains to prove that its addition and its scalar multiplication with this one vector is again belonging to W. First consider C into ft of alpha. Sorry. First we have to prove f of t plus g of t of alpha. To prove that f of t plus g of t of alpha is belonging to W. If we prove that f of t plus g of t of alpha belonging to W, that is f plus g of t of alpha is belonging to W, then we say that by the definition of S of alpha W, this f of x plus g of x polynomial is belonging to S of alpha W. Now consider f of t plus g of t of alpha is nothing but ft of alpha plus gt of alpha, since both are linear. Now, but we know that ft of alpha is belonging to subspace W and gt of alpha is belonging to W, and W is a subspace. As W is a subspace, then it is closed under addition. Then ft of alpha plus gt of alpha is belonging to subspace W, since W is subspace. As addition of these two, ft of alpha plus gt of alpha is belonging to W, then f of t plus g of t of alpha is belonging to W. Then by definition of S of alpha W, f of x plus g of x is belonging to S of alpha W. Now, let's see belonging to here be any scalar. Here be any scalar and f of here is belonging to S of alpha W. As fx is belonging to S of alpha W, then by definition f of T of alpha is belonging to W. Now we have to prove that same to fx is again in S of alpha W. Consider C into f of T of alpha, which is nothing but C into ft of alpha. But ft of alpha is belonging to W and W is a subspace, which implies C into ft of alpha is belonging to W, which implies C into f of T of alpha is belonging to W. Again, by definition of this S of alpha W, polynomial C into fm is belonging to S of alpha W, which is from definition of T-conductor of alpha into W. That is definition of S of alpha W. Therefore, this set S of alpha W is an closed with respect to the operations defined on the its vector space. Therefore, S of alpha W is an subspace of fx. So first part here, that is half part will be proved. Now we have to prove the remaining condition, that is f into g is belonging to S of alpha W. Whenever one of them is belonging to S of alpha W and another is belonging to ring of polynomials. Now to prove that S of alpha W is an ideal. Okay. Let fx, gx belonging to S of alpha W. Okay, as gx is belonging to, sorry, let g of x is belonging to, let g of x is belonging to S of alpha W, then by definition of S of alpha W, g of T of alpha is belonging to W. Let us take this g of T of alpha as a beta, which implies beta is belonging to W, since g of T of alpha is equal to beta. Okay, now let fx belongs to capital F of x and W is invariant under every polynomial in T, which is proved in previous part. That is, if fx is belonging to f of x be any polynomial, and we know that here we have proved that W is invariant under every polynomial in T. As W is invariant under every polynomial in T, and this beta is belonging to W, then f of T of beta is belonging to W. If W is invariant under every polynomial in T, it implies that if we take any beta belonging to W, then f of T of beta must be belonging to W. As fx is belonging to f of x be any polynomial, and W is invariant under every polynomial in T, and beta is belonging to W, then f of T of beta is belonging to W. But beta is nothing but g of T of alpha. T of alpha is belonging to W, which is nothing but f of T, g of T of alpha is belonging to W, which is nothing but f into g of T of alpha is belonging to W. Then by definition of S of alpha W, this polynomial f into g is belonging to f into g of x, that is fx into g of x is belonging to S of alpha W, which implies f into g is belonging to W, that is fx into gx is belonging to W, where g of x is an any polynomial belonging to s alpha w and fx belonging to capital F of x. Then by the definition of ideal, this s of alpha w is an ideal of a polynomial algebra f of x, which implies s of alpha w is an ideal in the polynomial algebra f of x, that is the ring of polynomial f, and which is the required result, and hence the proof. Okay. There is one remark. Fx, we know that Fx is nothing but ring of polynomials. A, it is a ring of polynomials. Now, and we know that in abstract algebra, field implies Euclidean domain, implies principal ideal domain, implies unique factorization domain, and which implies integral domain. In we know that that is field. If f is any field, then it is integral domain. If it is integral domain, then it is PID implies UFD, and UFD implies integral domain. As fx is a ring of polynomials, let f be a field. Let f be a field. If f is a field, then we know that fx is Euclidean domain. If f is not a field, then whether fx is an Euclidean domain or not, we don't know. But if f is a field, then f of x must be a Euclidean domain. As fx is a Euclidean domain, then Euclidean domain is a principal ideal domain, which implies fx is principal ideal domain. And we know that principal ideal domain is nothing but if an integral domain D is said to be principal ideal domain if its every ideal is a principal ideal, which implies every ideal E fx is a principal ideal. And we know that what is a principal ideal? Principal ideal is nothing but an ideal generated by single element. As each ideal of fx is a principal ideal, then every ideal in fx is generated by a single element, which is from definition of principal ideal. And in previous theorem we have proved that S of alpha w is an ideal of polynomial algebra fx, and as f is a field, then each ideal of this fx is generated by single element. As S of alpha w is an ideal of fx, then this S of alpha w is generated by a single element, which implies S of alpha w is generated by a single element. But S of alpha w contains the elements of the type polynomials. Then this S of alpha w is generated by some polynomial g of x, which is a single element, which contains all polynomials f1 x is nothing but g of f1 x into g of x, such that this f1 x is a member of ring of polynomial, which is from the definition of generator. Since S of alpha w is generated by a single element, and which element is nothing but this g of x, which implies gx is the generator of is the generator of S of alpha w. Now, this f1x is belonging to f of x. Therefore, there is possibility that this f1x must be a constant polynomial. Let f1x is equal to 1. That is, it is a constant polynomial. Okay. Then f1x into g of x is equal to f1x is 1 into g of x is nothing but g of x. Therefore, from this we conclude that g of x is the monic polynomial of lowest degree in S of alpha w. There is no polynomial which have degree less than this g of x and which is belonging to S of alpha w. Since g of x is the generator of this S of alpha w and this f1x is a constant polynomial, then f1x into g of x is nothing but a g of x. Therefore, this g of x is the monic polynomial of lowest degree in S of alpha w, which implies g of x is the polynomial of least degree in S of alpha w. In S of alpha w. Now, let f of x belonging to S of alpha w be any polynomial. Fx is belonging to S of alpha w, and we know that gx is the generator of this S of alpha w. Therefore, this f of x can be expressed as f of x can be expressed as f1x into g of x, something f1x into g of x, where f1x is belonging to f of x. Now, by division algorithm or by the definition of divisibility, this g of x divides f of x, which implies g of x divides f of x. Here we have taken any arbitrary polynomial which is belonging to S of alpha w. Then this generator g of x is belonging to then this generator g of x divides this polynomial fx. Therefore, from this we conclude that if f is belonging to S of alpha w, if and only if g divides this f. Otherwise, it is not possible that such a polynomial f is belonging to this S of alpha w. If we take any polynomial fx which is belonging to S of alpha w, then its generator polynomial g of x must divide that polynomial. And in previous above after after the definition of T-conductor of alpha into W, we have proved that minimal polynomial is always belonging to S of alpha W, as mx is belonging to S of alpha W. Then this generator polynomial g of x is also divides the minimal polynomials. Since any polynomial belonging to S of alpha w, if and only if its generator polynomial g of x divides that polynomial. As minimal polynomial is a member of S of alpha w, then g of x must divide that minimal polynomial. Next theorem. Let V be a finite dimensional vector space over the field F. Let T be a linear operator on V such that the minimal polynomial for linear operator T is a product of product of linear factors. Linear factors. That is P of x is nothing but x minus c1 to the power r1, x minus c2 to the power r2, and so on. X minus ck to the power rk, where each ci is belonging to field f, where I is running from 1 to 2. Okay. Let W is a proper subspace of V, which is invariant under linear operator T. Then there exists an vector alpha belonging to vector space V such that alpha is not in W, and second T minus Ci of alpha is in W. So here we have given that V be a finite dimensional vector space over the field F and T be a linear operator defined on that vector space V, such that the minimal polynomial for a linear operator T can be expressed as a product of linear factors, that is Q of x is nothing but x minus c1 to the power r1, x minus c2 to the power r2 up to so on, x minus ck to the power rk, where this each is ci where I running from 1 to k belonging to field F, and given that W is any proper subspace of a vector space V which is invariant under the linear operator T, then we have to prove that there exists one vector alpha belonging to V such that alpha is not a member of W, but T minus Ci of alpha is in W. Okay. Now we have to prove this. Given that T be a linear operator on finite dimensional vector space over the field F, and the minimal polynomial for T is a product of linear factors, that is P of x is nothing but x minus c1 to the power r1, x minus c2 to the power r2 up to so on, x minus ck to the power rk, where each ci is belonging to field whenever I am from 1 to k. Okay, and also given that also W is a proper subspace of as W is a proper subspace of a vector space V, then it is possible to choose then it is possible to choose a vector beta which belongs to V, but beta is not a member of subspace W. Since W is a proper subspace of a vector space V, then it is possible that we can find out one vector beta belonging to V, but which is not a member of W. Now let S of beta W is a T-conductor of beta into W, which is from definition of T-conductor of beta into W. Now that is S of beta W is nothing but it contains all polynomials belonging to this polynomial algebra Fx such that f of T of beta is belonging to W, which is from again definition. Let Gx belonging to this ring of polynomial Fx be a unique monic generator of the ideal S of alpha, and this one such a g of x is possible, since in previous remark we have proved this. There exists one generator for a s of alpha w. This, since this s of alpha w is an ideal of f of x and f of x is a principal ideal, therefore it is possible that there exists one generator for this one. Okay, now as g of x belonging to this f of x is a polynomial, then there are two possibilities for this g of x. Either this g of x is a constant polynomial or it is a non-constant polynomial. If possible, let us suppose let g of x is a constant polynomial. As g of x is a constant polynomial, then g of x is equal to constant term for all x belonging to this f. Okay. Therefore, g of x is equal to e. As this g of x is a generator of an ideal s of alpha w, then this g of x belonging to this s of alpha w. Therefore, as g of x is belonging to s of alpha w, then by the definition of this s alpha w, yeah, gt of alpha, sorry, gt of beta is belonging to w. As g of x is a generator of s of alpha w, which implies it is belonging to s alpha w, which implies gt of beta is belonging to w. But gt is nothing but g of t. It is a constant polynomial. Therefore, it is nothing but into beta, which is belonging to w. But we know that w is a subspace. As w is a subspace, then this beta is again is w. But but already we have assumed that there exists one vector which is belonging to vector space V, but which is not a member of W. But here we get this beta is belonging to W, so which is a contradiction. This contradiction is arises due to our wrong assumption. Which one is the wrong assumption? That is g of x is a constant polynomial, which implies g of x is not a constant polynomial. Hence, g of x is a non-constant polynomial. Constant polynomial. And here we have given that p of x is the minimal polynomial for the linear operator t, and in previous remark we have proved that the generator polynomial g of x divides the minimal polynomial. So here g of x divides p of x, and p of x is nothing but x minus c1 to the power r1, x minus c2 to the power r2, up to so on x minus ck to the power rk, where each constant term ci is belonging to f. As g of x is divides this minimal polynomial, then the nature of this the polynomial g of x is nothing but x minus c1 to the power something a1, e1 x minus c2 to the power e2, up to so on x minus ck to the power ek. Since g of x divides p of x, where ck or that is ci are belonging to f whenever I is running from 1 to k. And here we have proved that g of x is not a constant polynomial, as it is a non-constant polynomial, which implies at least one ci is positive. Sorry, at least one ei is positive, since g of x is a non-constant polynomial. Therefore, at least one of these even into up to one ek is a positive. Let us choose j such that ej is greater than 0. As ej is greater than 0, which implies x minus cj divides the polynomial g of x. Here we have assumed that the term ej is greater than 0, which implies the x minus cj must divide g of x. Then by division algorithm, or by definition of divisibility, then by division algorithm, this g of x can be written as x minus cj into h of x, where there exists one polynomial h of x such that g of x is nothing but x minus cj into h of x, where degree of hx is less than the degree of gx, which is from definition of division algorithm. Okay, therefore let us take this one as an equation. 1. Now, in remark, we have proved that g of x is the lowest degree polynomial in S alpha W. Therefore, here gx is the is monic polynomial of least degree such that gx is belonging to S of beta W. As gx is belonging to S of beta W, then by definition of S beta W, gt of beta is belonging to W. And we know that gx is the monic polynomial of least degree. And here we get by division algorithm, degree of h of x is less than degree of g of x. Therefore, as gx is the least degree polynomial in S of beta W, which implies hx is not belonging to S beta W. Since gx is the polynomial of least degree in S beta W and h of x is the polynomial of least degree in least degree than the polynomial g of x. Therefore, this h of x is not belonging to S of beta W, which implies from the definition of S of beta W, h t of beta is not belonging to W. Okay, let us take let ht of beta is equal to alpha, which implies alpha is not belonging to W. Let us take this one as an equation. Okay, now put x equal to t in equation 1. We get, put here x equal to t, then we get g of t. Put the x equal to t in equation 1 and operate g of t on beta. That is, if we put x equal to t, then it is becomes a g of t, and then I have to operate the g of t on beta. Then we get g of t, and we have to operate this on beta is equal to t minus cji of h of t of, we have to operate this on beta. Okay. Now g of t of beta, which is nothing but t minus cji of h of t of beta, which is nothing but t minus cji minus cji. But h of t of beta is nothing but alpha. Okay. Now g of t of beta is equal to t minus cji of alpha. That is, g of t of beta is nothing but t minus cji of alpha. But we know that g of t of beta is belonging to W. G of t of beta is belonging to W, and g of t of beta is nothing but t minus cji of alpha, which implies t minus cji of alpha is belonging to W, since g of t of alpha is belonging to W. Therefore, let us take this one as a equation 3. Now, from equation 2 and 3, from equation 2 and 3, here we get, which in from equation 2 and 3, there exists an vector alpha belonging to V such that alpha is not belonging to W from 2. Here one exists vector h of t of, sorry, h of t of beta, that is alpha, which is not a member of W, but t minus cji of this alpha is belonging to W. But t minus cji of alpha is belonging to W for some characteristic value Cj of T. Okay, which is the required result, and hence the proof. Thank you for watching the lecture.